Welcome back to Differential Calculus. In this video, I want to build up until we can get to the point where we are writing equations of tangent lines. I've talked a little bit about the idea of thinking of the slope between 2 points as a rate of change. If I jump over to Desmos here, I've shown you a graph that looks like this in previous videos, where we can control the position of 2 points and come up with the equation of a line between them. We can calculate the slope, and if we know the slope, we can find the equation of the line. Right. For any 2 points, that is what's known as a secant line. Our goal is to find a tangent line. A tangent line is a line which includes exactly 1 point on a graph, although that's a little bit misleading. If I jump back into Desmos, you can see even in this case of a secant line, I described this as including 2 points on the graph, the 2 points that we care about here, but there's also the point over here and the point over here where the line intersects the graph. That's kind of outside of our area of interest. We are looking specifically at this range where we are looking at the points. The line goes through the graph at this point and at that point. That's what we're talking about with a secant line. If we want a tangent line, what I'm looking to do is to take these 2 points and bring them as close together as possible so that when you zoom in, you can't really tell that the points are different. And if we can do this just right, then we can write the equation of our tangent line. Right. Before I get into how to do that, I do want to at least briefly mention the words secant and tangent. A lot of students have associations with the trigonometric functions secant and tangent for obvious reasons. The connection between the trig function secant and tangent and the secant line and tangent line is almost coincidental. In modern trigonometry, we define the trigonometric ratios based on a right triangle. At an earlier point in the development of trigonometry, the trigonometric ratios were based on the interactions between a line and the unit circle. And if you drew a line tangent to the circle at the point where the angle intersects with the circle, the distance between that intersection point and the axis along the tangent line is the value of the tangent function. It's absolutely true. It's not really what we usually think about when we think about tangent function, although it is what we think about when we think about tangent line. All right, so historically, there is a relationship there, but when we're talking about the secant line or the tangent line, we are not talking about trigonometric functions. So if I think about this, and I think about my arbitrary curve here and a couple of arbitrary points. Let's go with this point first of all. Let's give this point x coordinate c, and then its y coordinate will be the value of the function at c. And let's take another point here, x and f of x. If I take this second point and move it closer to the first point, then I will get something that is closer and closer to the tangent line. We know that we can calculate the slope between these 2 points. Y coordinates, f of x minus f of c, divided by x coordinates, x minus c. This is the slope of a secant line. To go from the secant line to the tangent line, we just want to move x as close to c as possible. We just developed this new tool for moving a point as close to another point as possible. M sub t, the slope of the tangent line, is going to be the limit as x approaches c of f of x minus f of c over x minus c. That is a perfectly working definition of the slope of a tangent line. This thing is also very important in other contexts that are distantly related, but we will try to build up based on the idea of a tangent line. This is also called the derivative of f of x at x equals c. I'm really not sure of the etymology of the word derivative, but it is the terminology we use, and we just kind of accept it at this point. To denote this, we'll, instead of calling it mt, you'll also see it called f prime of c. I don't really like the f prime notation all that much, but it is very common in the study of calculus and in a couple of other studies. But we put like an apostrophe after the letter f to say this is the function f, but slightly different. It's related to the function f, but it's not the same thing. F prime. This absolutely works. And theoretically, there's a lot of things we want to do with this form of the equation. Although when it comes to actually trying to evaluate these things, this form of the equation turns out to be kind of messy. And so we are going to change things up ever so slightly. We're going to have one point, x, f of x, and we're going to be moving to another point. And I can think about moving to another point by taking my x coordinate and just adding some little bit that I'll write as delta x. And so there's just a different way of pointing out my 2 points and then the distance between them is delta x. To find the derivative, the slope of the tangent line at point x, we use the same formula that I just slid off the screen. F prime of x is equal to the limit. I'll come back to the limit on what. Let's get the rest of it filled in first. I have f of x plus delta x minus f of x. Those are my y coordinates. Then I have x plus delta x minus x. Those are my x coordinates. And I mean, I guess that the limit here would be the limit as x plus delta x approaches x. That's following the same structure we had in what we were just talking about in the previous one. But if you think about that carefully, to go from x plus delta x to x, the thing that's really happening here is that delta x is going away. Right? If x plus delta x is going to x, that's equivalent to saying that delta x is going to 0. So if you just make delta x 0, then you get x. Then in my ratio, x plus delta x minus x, the x's cancel each other out, and we are left with just delta x. So there is a second form of the derivative. When it comes to working with these, the first version that I wrote down turns out to be far more useful when you are trying to come up with general rules for how derivatives work. We'll be looking at that throughout the next several weeks of this course. The second one is far more useful when you have a particular function and you want to know what is happening. So that's the one we're going to use in this video. For example, if I am looking at writing the equation of the line tangent to the function f of x equals 3x squared minus 4x plus 5 at the point x equals 3. The first thing I need in order to write the equation of a line is the slope of the line. And the slope of the line is equal to the derivative f prime at the point in question. And just following my formula here, f prime of 3 is the limit as delta x goes to 0 of f of 3 plus delta x minus f of 3 all over delta x. Right, so we want to evaluate the function. Plug in x equals 3. 3 squared is 9. 3 times 9 is 27. So we have 27 minus 12 plus 5, which is 20. Plug in x equals 3 plus delta x, and that gets a little bit messier, but we can manage it. So we'll have 3 times 3 plus delta x squared minus 4 times 3 plus delta x plus 5. Minus 20 all over delta x. Use the distributive property, clean this up a little bit. Go through all of the exciting algebra. And then we can combine some like terms. Let's see, I've got constant terms, 27 minus 12 minus 15. Coincidentally, that's 0. Okay, there's actually nothing coincidental about that. I've got constant term, or delta x terms, 18 delta x minus 4 delta x, not negative, positive, 14 delta x. And then I've got my 3 times delta x squared. That 0 in front kind of just goes away. Now I can reduce this fraction by canceling out some delta x's. And as delta x goes to 0, that term goes to 0, and we're just left with this term, which is 14. That was a very long way to go. But we now know that when x is equal to 3, f of 3 is 20, and f prime of 3 is 14. That's m. These are x naught, y naught. And with that, we can write the equation of the line. Y minus y naught, which is 20, is equal to m, which is 14, times the quantity, x minus x naught, which is 3. Distribute. Rearrange. And there's the equation of our tangent line. All right, so if I switch over to Desmos here, I didn't want me on the camera just yet. If I switch over to Desmos here, you can see that I have the original function f of x equals 3x squared minus 4x plus 5, the point in question, 320, and my tangent line, 14x minus 22, all graphed. If I slide this around a little bit, I can eventually get to the point where you can see that that is a point on the graph, and actually even this zoomed out for a pretty wide margin on the y-axis. The blue curve of the function and the yellow curve of the tangent line, I think those are blue and yellow, I'm colorblind, so I might be talking crazy. But those two curves are nearly indistinguishable. And if I zoom in a little bit, yes, you can kind of see down here near the bottom how they separate, sort of. But the further in you zoom, the more closely they look like they are the same exact curve. That's what we're talking about when we're talking about a tangent line. As we continue further into this course, we're going to be looking at tangent lines. We're going to be developing a more serious tools for finding equations of tangent lines, because while this process does work, it is notably cumbersome. For right now, it's what we've got, but we will develop better tools a little bit later on. We're also going to develop plenty of different applications where tangent lines are useful. For right now, let's just concentrate on making sure we know how to figure them out. So let me get my head out of the way, and if I can slide the screen down a little bit, let's come up with one for you to try. All right. I would like you to write the equation of the line tangent to the graph y equals 5 minus x cubed at the point where x is equal to 2. Right. Take a couple of minutes, see what you can do with that one, and I'll see you in the next video.